Hello, this Friday, 10 o'clock, 27th of September 2024. I wanted to get started on problem 5, though I don't think I'm really ready to do it, but let's see. First, the cusps. I thought we have f, but then it doesn't vanish at the other cusps, which cusp form must. And of course they lie in M2, gamma naught of 4. We got both of them. That's why I chose them, because then we can add and find one. Let's call it G today. 16 times f minus theta to the fourth. I think we've seen this function before in one of the problems in the last chapter. And then compute its values. So that's minus 1, naught, and unity. That's nice. And then when we multiply these two, fg, then we get a function in M8 of gamma naught of level 4. M4, sorry. And that means that multiplying by capital theta actually gives a cusp form, and that's 9 halves of weight 9 halves of gamma naught. So that's the first cusp form we can create. Capital C. And if we have any cusp, then we can divide it by this, because it's simple zeros. We should actually compute it just to check it. I haven't prepared for that. I don't even remember the coefficients of theta to the fourth. One plus, and then 4 times 2, that's 8. Q. And F is Q, and that means that 16 times plus etc. 16 times F minus, that gives 8Q. So it's a simple. It has a simple 0 at naught. That means we can divide by C. Then we get a modular form. So that means the cusp forms of level k halves is this function. I will just write the function. So that was my description of the space of cusp functions. And then to find the dimension, the first one, of course, is 9 halves. what I'm thinking about is it more simple just to find the formula, or should we use the formula for the dimension of this space, which is 1 plus k minus 9, this divided by 4, the integral part of that. I think we should do that. And then the question is, could we reduce that? We can take k minus 8 out. So that when we come to 9, it gives unity, and all the way up to c squared. Where we get c again, which is in 18 halves. That's 2.5. Where it raises to 2. That's not what this formula gives. What I'm saying is the dimension of, if k is 18, then the dimension becomes 2. And if we put 17 in here, if we put 16 in, it gives 1. If we put 17 in, then it gives 1 as well. Now, what am I doing? This is k. And if k is 17, then it's 2. I have to look a little more on that because I'm confused. I didn't want to start on B because I forgot what k regular cusps are. But the codimension, I thought that would simply be 1. Because if we have two modular forms that are linearly independent, then we can create a cusp form. So it should be 1, whatever k is, whatever integer k is. So I need to look at that as well. Hello again, it's now Saturday morning. I stopped because I guessed the number of k regular cusps could be no greater than 3, the number of cusps. And this, with this formula, the codimension would keep growing. I had a wrong intuition about the codimension, because in In M2 we have f, and if such a function was a modular form of the full modular group, then it would be a cusp form, but f is not a cusp form as it fails to vanish at the other cusps. Now, then I discovered I made a mistake here, applying the formula for the dimensions. This should just be 4. And that means we get 2 minus 2, so it becomes minus 1. And that means that the codimension is 1 plus k. Now, was that k? I'll just have to, 1 plus k fourth, the integral part of k over 4, minus, and we'll just have to write it for the various modular of k. So let's write k equals 4l plus naught, 1, 2, 3. So it's 2 every time plus L and then plus L minus 1, otherwise plus, minus, damn it. And this gives 3, 2, 2, 2. If we take the various values of k, 4l plus naught, 1, 2, 3, and then t to k, that's, we have 3, oh my gosh, so we have to do it vertically. So that means the number of regular cusps is 3, 1, 2, 1. As you can see, I've looked up the definition of a regular cusp. That's it's k regular when t to k is unity, and that's, we just count the number of unities here, and that's not really in agreement with what we get here. Now, I did do this from memory, so I just have to check that. And to do this, we can just prepare that. See. So we are in 13. Now what's that? That was just wrong. In 13 halves, there we have theta f squared g, theta f g squared. So we'll have to write up the first terms and then find the one where A1 is 1 and A2 is naught, so we have to find the next those terms and then a few more, and I'll just do that in Maple and then we can solve that. That's technique. But this, either this should just be unity or there's some more I don't understand. It's now Sunday afternoon and I've worked a little on this problem. First, I checked the value of naught. I actually did the calculation again, and I'm really not sure if you can see it, but I did it once again, and it turned out that t value here was unity, which means that we agree this column equals this column. Another thing I noticed watching the video, I checked the video for this, I didn't find it, that I did it correctly though, but I've done it now, and is that I wasn't able to see the cursor on the screen. I don't know it's out. I checked some settings and maybe I've solved it. Next, we do this in Maple. And first I define theta, and then theta to the 4th, and truncate it up to q to 10th, and define f. Then yeah, that was what we had to multiply by, as it says here. So we get the first cusp form in m 4.5, that's in m 9/2. And then we go to the two cusp forms generating m 13/2. They are here. And of course, this being a product of f and f has the leading term 2q squared, so it's easy to find one where we get 1 and naught, which we have here. So that's the formula written out for it, and a1 is 1, a2 is naught, a3 is naught, and then a6 is naught. I don't know how it continues, but here's the formula for it, and that should actually solve problem 5.